Hello everyone, welcome to the session 1 of week 2. We will talk about more additive technology landscapes and specifically we'll go into details of powder bed fusion called PBF. We'll learn what is exactly laser powder bed fusion and electron beam based powder bed fusion. What are their applications and what are the value additions? You may have also learned already in the previous lectures about various other 3D printing technology recognized by ASTM. You may have already learned about VAT photopolymerization, material extrusion, material jetting and binder jetting. In the upcoming lectures, we will learn about powder bed fusion, direct energy deposition and sheet lamination. And just to remind you, the ones which are shown using these blue squares, those are available with Wipro and they use them in regular basis. The one which is highlighted is what we will discuss today. The powder bed fusion process is offered in 3 forms. One is laser based powder bed fusion, there is multi-jet fusion and there is electron beam based powder bed fusion. So here is the working principle for powder bed fusion. In powder bed fusion, the material that we want to fuse in form of 3D object is spread on a build platform and it is melted using laser or electron beam selectively as desired and planned in a CAD file. The beam fuses successive layers of powdered material. Again, the material can be either metal or a polymer and thus we create a 3-dimensional object. The powder bed that it serves as a raw material because it has to be fused using a laser beam or electron beam. It also supports the part that is being built, right. A schematic of this process is shown on the right bottom. There are 4 major components that we need to pay attention to. One is the powder of the material which is either metal or polymer, which is shown here in the reservoir and at the center in the build platform. The central part is the build platform marked as 2. The recoater is on the right side, number 3, and number 4 is the laser source. As I mentioned earlier, as the process is continuing, the build platform goes down depending upon what layer thickness we have chosen. The metal powder reservoir or polymer powder reservoir, it is pushed up so that one layer of powder is created here. This layer of powder is pushed by the recoater on top of the build platform and thus after that everywhere there will be a spread powder which will be processed using this beam of laser. This process has several advantages. For example, as we now know, complex geometries can be printed. We can use various materials to build 3D objects as our application needs. We can use polymers and various types of metals and alloys. There is minimum material waste because whatever extra powder you see here can be collected and can be removed after the part has been made completely. It is recycled after some processing and we will talk about it in coming slides. This process can be used for rapid prototyping or for real application parts. However, there are some limitations as well. It takes enormous time and effort and investment to create a setup so that it is ready for building a sensible part of the desired quality. So, there is some cost involved in it. It definitely takes some post processing. You have seen already that there is some extra powder particles stuck around the geometry. Those particles need to be removed, and sometimes there are some support structures of the same material which are unwanted in the application. Those structures need to be removed. Since we have limited space in the chamber, and there are limitations of the power of laser and the way it is controlled, there are always some size limitations about the object that needs to be printed. There are always some health and safety concerns, because in this process we are dealing with the powder. Powder particles are very fine particles, and as we handle, they can influence our respiratory system. Here are some examples of manufacturers of LPBF. There are various companies that make such machines. There is 3D Systems, EOS, SLM Solutions. There is Arcam, that is a GE company, Amaze, and Intech Additive Solutions. As we know already, various metals and alloys can be printed. For example, aluminum alloys, copper based alloys, stainless steels, various titanium alloys, various precious metals can be printed, and definitely various types of polymers can be printed. There are versatile applications that can be built using this powder based process. We can create complicated fluid and heat channels. We can create various biomedical implants. We can have even more complicated high energy structures, for example, turbine blades. We can also create various components of heat sinks and channels. Now, depending upon the energy used in the process and the raw material that is used, we have categorization of this powder bed fusion process. Based on the raw material, we can have polymer based process or metal based process. We can have, based on energy, a laser based process or electron beam process. Usually electron beam process involves higher energy, the interaction volume is larger, and higher temperature can be achieved as compared to laser based process. Various manufacturers have various brands of machines, and depending upon that and the applications and the customers, there are various models of these machines. For example, EOS offers various machines like EOS M280, 290, 400, and as we know, M280, 290 can be used for medium sized parts, for example 250 mm, and so EOS M400 can be used for larger parts. There are various other brands, for example Concept Laser, Renishaw offers various models of machines, SLM Solutions has various machines available. There are various solutions available from GE Additive, 3D Systems, Stratasys, HP has metal jet systems because of their historic involvement in inkjet printing. We have desktop metals available in various forms and models. Mark Forged, Exact Metals offers various solutions. We have Ultimaker and Velo 3D. Depending upon the laser that is used and various metals and alloys used, there are various parts, different types of parts for various applications that can be built. In some applications we need high precision, in some parts we need larger volume or high throughput. Sometimes the geometries are very complicated, sometimes we are using precious metals, sometimes we are using the other metals which are more engineering type. EOS M290 can build a medium sized part. It offers high precision. There are various monitoring systems that are used in these machines. Some machines do offer open source monitoring system. Some have their proprietary monitoring systems. For example, EOS machines use EOS state. There are various types of connectivities possible in these machines. Some machines use fiber laser, some machines come with quad laser system in which 4 lasers can work simultaneously, and by doing that we can either create higher power so that difficult to melt materials can be fused and those parts can be made, or those 4 lasers can work simultaneously at different locations, right. Depending upon the choice of laser and the build size and the control of laser, we can create compact sizes and various topologies as mentioned earlier. Here are 2 examples of machines from EOS. One is EOS M290, the other is EOS M400, and there is another version of EOS machine M400 which is called EOS 404. We have compared these 2 machines using various parameters, for example, printing technology, build volume, laser power, recoating direction, gas flow, we have powder feeding technologies, various types of connectivities, and what other features are available. Both machines use DMLS, which is direct metal laser sintering. EOS M290 can print medium sized parts. M400 and 404 can use larger parts. The power of laser in M290 is 400 watt. In M400 we have 4 lasers of 400 watt each, or we can get a single laser of up to 1000. The recoater in M290 goes from left to right. In the machine which makes larger volumes, which is M400, the recoater goes from back to front, if we see from the front view. The gas flow is very important in certain gases. For example, inert gases are used. In EOS M290, the gas flow is from back to front. In EOS M400, it is from side, but in EOS M404 it is from top. The powder feeding in M290 is against gravity. The powder is pushed from bottom to top, and in EOS M400 it is spread on top of the build part. Various connectivity are available. Both machines in this case use Ethernet connectivity, and there is a proprietary EOS print software which connects the machines with the computer for control and things like that. These machines offer various inert gas atmospheres, for example argon and nitrogen. They offer real time monitoring, high precision and good surface finish. Gas flow is an important parameter that decides the quality of the printed parts. Depending upon the quantity, the amount of gas flow and the direction of gas flow, the part can have homogeneous properties, more bubbles and so on. In EOS M290, the gas flow is from back to front. In M404, the gas flow is from top. Since we are using 4 lasers and total power involved in M400 is higher, we want the gas to be homogeneously distributed, and we don't want any heterogeneity caused by the rate of gas flow in various parts that is being built, and also we don't want the byproduct gases that are coming after fusion to interact differently at different part of the build part or the component. The larger machines, since are able to build large components or parts, it is at times useful to have a central supply of gas flow as it is in EOS M400, so that gas comes from top to bottom and is spread everywhere, and all the smaller parts that are being built have the sufficient supply of the inert gas or nitrogen, whatever is being used is available to them. In smaller chamber machines like M290, the gas flow rate does influence. However, since the chamber size is small, the gas whatever comes from the back side will be in shorter amount of time will be spread homogeneously in the chamber. So, the properties are not affected that critically. Similarly, the machine recoating is also very important. In EOS M290, the recoater moves from left to right. In EOS 400M machine, the recoater moves from back to front. So, it takes fresh powder from back to front and then it goes back, which is it is resting position. Similarly, the powder feeding is also important when we are doing 3D printing, and powder feeding can be different in the machines where we are building medium or smaller parts as compared to the machines where we are making larger parts or larger volumes. In EOS M290, the powder is fed using a reservoir that we saw is on the right side. The reservoir platform moves up, a layer is formed which is pushed to the build platform, right, and the powder can be fed in this reservoir for one build, one complete build, since we are making medium or smaller volumes. In EOS M400, since we are building larger volumes, we would like to avoid storage of larger powder volumes in the machine, because the machine will have to be bulky. For that, the chambers will have to be large. To avoid that, what is done is that once a powder has been used, it can be taken out of the machine and can be sent to a powder chamber or powder station, where it can be assembled to a powder cleaning or rehabilitation assembly. It can be deoxidized or dried, and from there it can be sent to another powder station, which is the intake powder station for the machine, and can be fed again to the machine while the printing is going on. This is much needed because by doing that we will not need a very large quantity of the powder available for the same session of printing. All this operation can be fully computerized, fully automated, and depending upon what is the volume of the build needed, what is the speed of the build, the powder supply can be made available unhindered without any human intervention. Now let us learn about electron beam powder bed fusion. The working principles are similar to laser beam powder bed fusion as far as the movement of beam and spreading of powder is concerned. There are subtle differences that we will talk about. In PBF-EB, which is powder bed fusion based on electron beam, the melting of metal powder is done by exposing it to a beam of electrons, and before we start printing, the thin layer of powder is spread and it is preheated by exposing the entire layer to a stream of electrons. This broad exposure of electrons heats the powder to appropriately high temperature, so that a better melting or higher temperatures can be achieved overall. A schematic of this process is shown on the bottom right. The main parts of this setup are a vacuum chamber, of course, because we are using electron beam for melting. We have electron beam shown in the green color. We have metal powder, which is the light gray color. We have a build platform like we had in laser beam fusion process. We have a recoater, right. So, like in laser beam based process we had advantages and limitations, here too we have some. We can definitely print complex geometries. Since we are using preheating and we are using electron beam, we can reach higher temperatures, and since we have higher temperatures, we also have the temperature steady for longer time. So, the residual stresses are not as much as they are in laser based process. Also, electrons have much larger volume of interaction with the metal powder. So, the pool is larger, the metal pool is larger, and that maintains the temperature. So, the stresses have enough time to get released from the build part. Since we are using a vacuum chamber because of electron beam, the metal powder does not oxidizes. So, various oxides and other unwanted precipitates etc., they are not formed. So, we have less impurities. Along with all these advantages, we also have some limitations. Since the temperatures are higher and vacuum is maintained, the cooling times basically are also larger. So, we have to wait between two consecutive builds. Since electron beam is used, again only conductive materials can be printed using this process, and since the interaction volume of electrons is much larger as compared to laser, we can achieve less accuracy. So, individual ligaments or layers that can be printed using this process are larger than what we can achieve using laser based process. Here is a closer look at the electron beam melting setup. We have various critical components. For example, we have electron beam column, which houses a filament where the electron beam is generated. We have a series of lenses which contains astigmatism lens, we have focus lens, we have deflection lens. These lenses are important because they control the shape of the electron spot, beam spot that we get on the build platform, and these lenses also control the speed and direction and precision with which the beam is moved on the build platform, so that we maintain the quality of the build part. We have focus lenses which control the diameter or the size of the beam, and we have deflection lenses which help move the beam on the platform. Astigmatism lenses are also important because they control the blurredness and the shape of the beam. These beams can be used to create a circular beam instead of a stretchy beam spot that we get on the powder bed. Since this process generates higher temperature, we maintain the temperature using heat shield, so that less energy is used for printing. Overall, the preheat basically is maintained using these heat shields. We have a vacuum chamber because of the electron beam involvement, and the red line, as mentioned earlier, this red beam is the electron beam. The rake or the recoater is shown here. We have powder, the part is this as shown here. We have the overall build tank, the start build plate or build platform is here, and the build platform can move up and down like we had in the laser based printing as well, right. So, to summarize, this process also is a selective melting process where the melting is done using electron beam. The feedstock is a powder bed. That means we first spread the powder and that powder is melted, is fused using laser beam, the electron beam. Various materials, metals and alloys can be used for printing. We can use titanium, especially titanium and cobalt and chrome, because they oxidize, and laser based process is not preferred. If possible, electron beam based melting can be used because it offers vacuum, so there are less chances of oxidation, no chances of oxidation. Various nickel superalloys can be used. The layer thickness that we can achieve in this process is about 50 to 200 microns, which is larger than what we can achieve in laser based process. The spot size is also larger, 140 micron to 250 microns, which is larger than the what we get in laser based process. And since we have a vacuum chamber and electron beam, we typically cannot make very large parts, 250 mm to 430 mm for this particular setup, because it is difficult to maintain vacuum in a larger volume. So, we have learnt two powder bed fusion based method today. One is a laser beam based process, the other is a electron beam melting based process. We will learn about sheet lamination and direct energy deposition in the upcoming lectures. Thank you for listening.